So here I'm going to talk about the theory from chapter 11, and I'm only going to focus on the parts of chapter 11 that that we're interested in. There's an opening on stress and strain. We don't care about that. We're going to begin with periodic motion. So we're going to begin with section 11.2, periodic motion. If you can read that. Periodic motion occurs when there's some behavior that's repeated in a very orderly way. There's a couple cases that we're most concerned with, and one is a pendulum. And so if you had, some ceiling, some overhead support, and you suspend a weight, a mass, from a cord that's attached to that ceiling, this thing will swing back and forth in a very periodic way. At any given instant in time, that cord is going to make an angle theta with the vertical, and like I said, there's a mass attached at that point. So if you look at this pendulum, it's like any pendulum you've seen. It swings back and forth. In a perfect world, it would just keep going back and forth. Of course, because of friction, it'll be reduced in a way. But for the things we consider, we're going to have a perfect pendulum that'll just oscillate back and forth for infinity. Another type of simple oscillator that occurs, and it's very similar to the other one in the dependence on time of this back and forth motion, is going to be a mass attached to a spring. So if I take some mass, and I'm assuming that this is a frictionless table, and I attach it to a spring, and I pull that spring out from some relaxed position, this x equals 0. What I find is this mass, if it's out here to the right, it's going to experience a force that restores it towards the center, and it'll start moving towards the center, and then it'll reach this point as it gains velocity, and then it'll begin to compress the spring, and it'll slow down. And so what happens is this mass just oscillates back and forth in time in a periodic way. So what we want to talk about is simple harmonic motion. And this occurs when the restoring force of some system is proportional to its displacement. That should sound familiar because you know that for that spring, there's going to be a spring force, and it's going to be equal to K delta L, where this is some spring constant. And delta L is some displacement from equilibrium. So if we put all this together, we're just going to redraw this little simple spring system and talk about the force that it experiences. I'll just draw it out one more time. Again, x sub naught equals 0 is the equilibrium position of that spring. And notice that I've gone and pulled that mass out to some other x like this. So the restoring force, F of x, is just going to be minus K times x. And notice that that minus sign creeps in here because I've decided this is my positive x direction. And when x is positive, when I pulled that mass out to that right-hand side, that restoring force is towards x equals 0, towards that center. Like that. So you know that with this expression, that mass on this frictionless table is going to experience an acceleration. So remember, from Newton's second law, F equals ma. And since all these things are happening in the x dimension, I'm going to say F sub x equals m a sub x. This allows me to write a sub x equals the force applied divided by the mass, which should look very familiar to us. And if I plug in that restoring force from that spring, I get minus kx over m. And it's interesting, like when you look at this expression, you'll notice that when x is positive, the acceleration is going to be negative. So if I pull x Now, if I pull that mass to the right of the equilibrium position, it's pulled to the left. If I push it to the left, then the restoring force of that spring is directed to the right. And that's what causes this oscillatory motion. So if I look at the this behavior of this mass in time, and I'm going to draw it for a third time like this. What I notice is I'm going to call this vertical line my x equals 0 position. I'm going to say that I'm going to pull this mass out initially to a distance a to the right. So we'll say this is some a out here. And the reason we're writing a here is because we're going to call that the amplitude of the motion. If I pull that mass out to a distance a to the right and release it, it's going to go, sliding towards the center. Then the spring's going to compress and it's going to slow down. It's going to go some distance to the right and it's going to be pushed back and it's going to come back out and it's going to come out to that same distance a from center. So this distance a is going to be the amplitude of the motion. It turns out, because this is a little symmetric problem with this spring, that restoring force is proportional to k times whatever your displacement is. It turns out that the farthest this mass is going to go to the left is minus a. So anyway, we start out and we release this object, this mass, v sub x equals 0 when we let it go. But the acceleration is towards the center. Then it flies towards the center and eventually it gets there. And once it's here, well, it's got a velocity now in the x direction. It's still moving to the left, but the acceleration is going to be 0 because the displacement from the spring's equilibrium position is 0. And if you let this mass keep going, it goes all the way to the left and it comes to rest again. But because it's been displaced to the left of equilibrium, it is going to have an acceleration back towards the equilibrium position. And so it goes to the far left-hand side, stops, and then it moves to the right again when it hits equilibrium. Again, a sub x equals 0 because the spring is relaxed and happy, but you've built up this momentum, you've built up this velocity. And this is this behavior that's going to be repeated over and over again with this mass just going back and forth. Now, the quantities that describe this motion, which we call simple harmonic motion, are going to be the following. And I'm going to write quantities in SHM, that being the abbreviation for simple harmonic motion. And the first is that amplitude. And that's just the maximum distance that the object reaches from its equilibrium position. It's going to go just that far one way or the other. A cycle is going to be a complete round trip. When it goes, I pull it all the way to the right, I let it go and it goes to the left and back again. That's one cycle. So that's a complete round trip. Then the period is going to be the amount of time that it takes to complete one cycle, and we use a capital T for that. And that should be a familiar word because we used period to describe the orbit of planets in 131. Then we have frequency, and frequency is just, the amount or the number of cycles you complete in a given amount of time. And for this, what we're going to call it F with the little f. The units are going to be a cycle per second, which is also, because a cycle is basically a unitless thing, we could call this inverse seconds, and that is also a hertz. After Heinrich Hertz, a German radio scientist. So now we say, all right, I got amplitude for this motion back and forth. I know it's completing this full cycles. The period is how long it takes to complete one of those. The frequency is F. This frequency and the period are related to one another by a very simple expression, F equals 1 over T. And from that you can see, oh, T must be equal to 1 over F as well. So hold on to that. And then the last strange quantity, which you're going to use, is the angular frequency. And for that symbol, we're going to use omega, and we're going to say that the angular frequency is just 2 pi times that regular frequency. And in units, we're going to call this radians per second. It's interesting because it looks like it's a frequency and you might want to use hertz, but you don't. You want to use radians per second when talking about angular frequencies, just by convention. And because the frequency is 1 over the period, I can write it like this. So notice these are the quantities of simple harmonic motion, and they're going to form the basis for what we discuss in this part of this chapter.